Hello, in this video we're going to discuss nuclear energy and the processes that create it. So first we'll just simply talk about chemical reactions and the energy associated with, for example, an exothermic chemical reaction. In those reactions, there actually is a mass loss that occurs, but it's a loss that can't be measured. And we indicate here on this particular slide just how small that mass loss is. That is then converted to the energy that we might observe in, say, a combustion reaction. And, of course, the amount of energy that's generated goes by the famous Einstein equation equals mc squared. So, again, the point is that chemical reactions generate far less energy than a nuclear reaction because the mass loss is much smaller by an enormous amount. So in these reactions, we are talking about converting mass to energy through the equation E equals mc squared. And just to provide some kind of context here, we can take an example of a 1 kilogram of mass of any substance. If all of that is converted to energy, again, using the equation E equals mc squared, we would generate 9 times 10 to the 16th joules. Now, just to put that in perspective, if we burned 1 kilogram of gasoline, which is, of course, a chemical change, and we know that combustion is simply the reaction with oxygen. For hydrocarbons, the products of complete combustion would be carbon dioxide and water. The amount of energy generated is 4 times 10 to the 7th. Now, if we just compare this, we're talking about 10 to the 7th versus 10 to the 16th. That is an enormous difference. And again, as I noted before, the mass lost in a chemical reaction is something that we can't measure because you remember that we always talk about chemical reactions and conservation of mass. And the reality is that mass is not conserved, but mass energy is conserved. All right, so let's talk about nuclei and nuclear reactions and what's going on here that creates all of this energy. So the first thing we're going to note is something called a mass defect. And this is a difference in the mass of the actual nucleus and its constituent nucleons. So, for example, if we took all of the neutrons and protons in the nucleus and added their masses together, we'd find that the sum of all those masses of neutrons and protons is actually greater than the mass of the nucleus itself. So let's repeat that. The mass of the neutrons and protons in the nucleus, if you were to isolate them and just measure their masses, the masses of the individual neutrons and protons, when we add them all together, is actually greater than the mass of the nucleus itself. The mass defect is then the difference between the mass of the nucleons and the mass of the nucleus itself, and that's greater than 0. So what's happened to that mass? Well, as you probably have guessed by now, it's converted to energy. And again, using E equals mc squared, so the mass defect represents the energy that's released when the neutrons and protons come together to form the nucleus. All right, so just to give you some examples here of nuclei and the mass defects, we can see that, for example, in the case of helium, the helium-4 nucleus mass, if we add all the neutrons and protons together, 2 neutrons and 2 protons, that would be the mass. And so there's a difference here, which is the mass defect given in atomic mass units. Converting that to energy, all right, this is what we have here. It's on the order of 10 to the minus 12, and that, of course, is per nucleus. So each nucleus, that's the energy that's released when that nucleus is formed. And then one thing that's actually quite telling about the stability of the nuclei is the energy per nucleon. If we do a comparison here of various kinds, so here's iron 56. We also see the mass defect shown here with that, and then of course uranium 238. So we'll see in this grouping the iron 56 nucleus actually has a larger energy per nucleon. Now, if we put that on a curve, this is what's called the curve of the binding energy. So this binding energy is the energy that is released due to the mass defect when the nucleus is formed. And the first thing we'll notice is in this curve of the binding energy is that the iron-56 nucleus is the largest, and that means it's the most stable. The more energy that's released when the nucleus is formed, the more stable the nucleus itself. So iron-56 sits atop the curve as being the most stable nucleus. Now, if we look at the curve, the area that's shaded yellow on this particular curve, what we'll note is that these are, of course, the heavier nuclei, and we'll notice that the binding energy actually falls off as the mass number, as the mass of the nucleus itself increases. So on the yellow side of the curve, we see a decrease in the binding energy as the mass increases. And on this side of the curve, this is where these elements are going to be such that nuclear fission would actually increase stability and release energy. So on the yellow side, nuclear fission, which involves nuclei splitting into smaller nuclei. When that happens, we're going to note that we're going from larger nuclei to smaller nuclei, and the smaller nuclei have a higher binding energy, and so that means that energy is released as we go from the larger nuclei to the smaller nuclei, again because the smaller nuclei have a larger binding energy. And that then is how nuclear fission generates energy. So, for example, uranium-235 is a fissionable isotope. It is actually a minor isotope of uranium. 238 is the most stable isotope of uranium. Uranium-235 only comprises 0.72% of the uranium that exists in nature. So this diagram shows one example of the nuclear fission of uranium-235. There are many different possible outcomes to this, but in this particular example, we have a neutron bombarding a uranium nucleus. So there's our neutron, of course, bombarding our uranium nucleus, and that neutron is absorbed, temporarily forming uranium-236 because we've increased the mass number by 1. Now this destabilizes the nucleus, causes change shape, and what will happen is it will then split, all right, and break apart into two smaller nuclei, in this case krypton and barium. Now again, the products can vary quite a bit, so this is just one example. And along with that, we produce 3 additional neutrons. Okay, so kind of summarizing, here's the nuclear reaction that's depicted in this illustration. What's actually key to this, and this is something that when we talk about nuclear energy and reactors and explosives, that we actually get a situation where we have 1 neutron absorbed and 3 neutrons produced. So this actually can lead to a chain reaction. Since 1 neutron is absorbed and 3 neutrons are produced, the 3 neutrons that are produced can go on and induce fission in other uranium nuclei, and this becomes a geometric process that the chain reaction that results can lead to a lot of energy. And that's something that we'll talk about a little bit later on in another video. And so, for example, in this particular case, for each nucleus that's split, form the krypton and the barium, we get a release of 2 times 10 to the 10th kilojoules per mole. And so roughly 1 kilogram, and we're rounding off here, but if we take 1 kilogram of uranium-235 undergoing this particular fission reaction that releases the energy given here, which is comparable to 33,000 tons of TNT. So you can see how just 1 kilogram fissioning can generate a huge amount of energy in these kinds of processes, and that's, of course, the origin of the power of these nuclear explosives. All right, so moving back to the curve of the binding energy, we're going to look at the left side of the curve in the kind of the purple area. And this side of the curve, what we'll notice is that the increase in the binding energy occurs as we go from small to larger nuclei. So, for example, going from hydrogen to helium, that means that the process that is favored and releasing energy is a fusion process where we're fusing smaller nuclei together to form larger nuclei, and that will result in the release of energy. Now, what's key to this is that the curve is actually much steeper on the left-hand side for fusion than it is on the right-hand side for fission. So fusion can therefore release a whole lot more energy than can a fission reaction. And of course, this is the energy that's used to power stars, nuclear fusion. When we talk about the so-called hydrogen bomb, we're talking about explosives that rely on fusion energy and are therefore much more powerful than the fission bombs which were used in, for example, World War II, dropped on Hiroshima and Nagasaki. So this slide shows the fusion reactions that would occur in our own sun, which is roughly, as indicated here, 73% hydrogen, 26% helium. All right, and this just simply shows how these reactions, there's a mechanism here indicated for the reactions where ultimately the result is the fusion of hydrogen nuclei, or protons, obviously, to form helium-4. And there's a tremendous amount of energy released there, and that, of course, is what powers the sun. So as long as we've got sufficient hydrogen present within the sun, then the sun will continue to generate energy through fusion. Once the hydrogen fuel runs out, then another set of processes occur that will be a discussion for a later date. So here we see an illustration of the process described on the previous slide, where the overall reaction essentially involves 4 protons coming together, fusing, producing a helium-4 nucleus with 2 neutrons and 2 protons, and also 2 positrons. We'll note, of course, that what this means is that protons have been converted to neutrons. So each proton is converted to a neutron and a positron. We'll notice that there's charge balance. On the left-hand side, we have a total charge of +4. And on the right-hand side, the helium nucleus is +2, and the 2 positrons are +2. So we have a total positive charge of +4. If we compare the masses, the 4 proton masses are indicated here, and the mass of the helium nucleus is indicated here. Of course, positrons having the same mass as electrons are insignificant mass-wise relative to the masses of the protons and the helium nucleus. Much, much smaller mass. The total mass difference is given here, so there's our mass defect, and that gives us, in terms of kilograms per fusion process, 10 to the minus 29, which is obviously pretty small. If we do an E equals mc squared, though, that's 10 to the minus 12 joules. And then if you start thinking about numbers, that, for example, if we had a mole of helium-4 nuclei produced, exactly how much energy that would produce is quite significant. So this is a process that generates an awful lot of energy. So this concludes our discussion of basic nuclear energy through fission and fusion. In the future, we'll continue discussions of uses of nuclear energy.